Okay, we are going to look at how to work a weak acid problem. Very well could have one of these on the exam. This is a homework problem, problem 10.66. So here is the problem straight. I screenshotted this right off Mastering Chemistry. It says about 15%, and your numbers may vary slightly. Sometimes they do that, but mine says about 15% of the acid in a 0.0 or 0.1 molar solution of a weak acid disassociates to form ions. It says you may want to reference certain pages in the textbook while completing this problem. So the first question is, what is the concentration over here, part A, of H3O plus? All right. So if you remember, we need to write an equilibrium expression for this. We have Ka. If we have some weak acid, well, let me write the equation first. So we don't know what weak acid it is. It just says Ha plus water. It's always in an aqueous solution. Double arrow, because it's a weak acid, makes H3O plus, because this is the base. So the lone pairs on water are going to grab the hydrogen from the acid. Plus, we're going to make A minus. And when we write Ka, remember we leave water out of it. So we'll have concentration of H3O plus, which is what we're looking for, times the concentration of A minus divided by the concentration of HA. Okay. Now, this is actually what you would use if I gave you what weak acid it was. Like if I said you had a 0.1 molar solution of acetic acid, or I told you what the acid was, then you would go find the K and plug it in. But because it tells us the percent, we actually may not use Ka here. So we can calculate the concentration of H3O plus if we have, didn't mean to select that. If we have initially, I'm going to scoot, well, can't scoot it down. Initially, we have 100% of this. And it says what we end up with is 15% here and 15% of this. Now, when 100%, what is 100%? It is 0.10 molar. That represents 100% of the acid. That's what we have. We have a solution that's 0.1 molar. So that represents 100%. So 15% of 0.1 molar is going to be what we end up with for our products. So the concentration of H3O plus is going to equal 15% of 0.1 molar. So how do we find that? We will simply do 0.15 times 0.1. And you should get that the concentration of H3O plus is equal to 0.015 molar. So that's what you would write in here, 0.015 molar. It says use two significant figures though, so you'd say 1.5 times 10 to the minus 2. Then what is the OH minus concentration? How do we find that? Let's get this over here. Get this over here. Remember, we're going to use Kw. So Kw equals the concentration of H3O plus, or just H plus, times the concentration of OH minus. So we know Kw, and now we know H3O plus. We're going to solve for OH minus. To do that, you divide both sides by the concentration of H3O plus. Those cancel. So what that is going to be is 1 times 10 to the minus 14. That's Kw. Divided by now 0.015. And you should get that that equals 6.67 times 10 to the minus 13. Molar, that is the concentration of OH minus. And then part C says, what is the pH of the solution? How do we find pH? Remember, H3O plus, the concentration of it is synonymous with just saying the concentration of H plus. And pH, so this is for part C, equals the negative log of the concentration of H plus. So we're just going to plug this in for the concentration of H plus. So you do pH equals the negative log of 0.015. and I got 1.8, 2 decimal places, so 1.82 for pH. So there's one example of a weak acid solution or weak acid problem, but I'm going to go ahead and walk you through another one really quick. Let me open up a new note. So if I said that you have 0.15 molar solution of, let's just say, what's a weak acid? I'm going to scroll up. I think we're all the way at the end, so I'm going to scroll way, way, way up. I'm going to go to the weak acid table. We're just going to pick a weak acid off of that table. I think we passed it. After acid-base strength, right here. So looking at this table, let's just say we have 0.15 molar of hydrofluoric acid, HF. The Ka is 3.5 times 10 to the minus 4. Of HF, whoop. I don't know why it's not writing for me. Okay, of HF. And the Ka is 3.5 times 10 to the minus 4. And then I want to know question 1, what is the concentration of H plus? And then 2, what is the pH of this solution? Here is where we will use Ka. Ka equals, it's going to be, so we need the equation, we need the first thing you'll do is write out the dissociation of HF in water. What does it give you? HF is the acid, so it'll give you H3O plus, which is just like saying H plus, plus the concentration of F minus. So Ka is going to be equal to the concentration of H plus or H3O plus, either one, times the concentration of F minus divided by the concentration of HF because we leave water out of it. So we know the concentration of HF already. And remember, the concentration of H3O plus, this guy, your two products are going to be identical. Every time one hydrogen is traded over to water, we create one of each thing. You can probably hear my son. So we can call the concentration of both of these things X. So if we plug those into Ka, we can now say equals X times X over the concentration of HF. And remember, we know what that is, so we can plug that in. So Ka, goodness gracious, Ka is equal to X squared over, now I'm going to plug it in, 0.15. All right, and you know Ka, so we're going to plug Ka in as well. So it becomes 3.5 times 10 to the minus 4 equals X squared divided by 0.15. Someone's not happy. I'm almost done, bud. All right, so from here, you would solve for X. I may have to end this sooner than I thought. Here, you would solve for X. Okay, so multiply both sides by 0.15. And then take the square root of all of that, and that will give you X. Okay, X is the concentration of H plus. So that will answer number 1. You're going to have to calculate that out because I'm about to go. And then pH, question number 2, is just the negative log of what you solve for X. All right, I hope that was helpful. Definitely want you to know how to do this for the exam.